SwayamPrabha. Digital India. Educated India.
Welcome back. We were discussing in the last lecture about Exergy, okay, which is nothing but availability or available energy or useful work potential. Okay, so in this particular lecture, we will be looking at specifically Exergy of a fixed mass or closed system. Exergy like energy can be transferred to or from a system in three different forms, that is heat, work and mass flow. Okay. Now let's first look at Exergy by heat transfer. Now heat, as we know, is a form of a disorganized energy, and not all amount of heat can be transferred to a work. Okay. Now if you consider or make use of a reversible heat engine, then the maximum amount of heat can be transferred to a useful work is simply efficiency of a reversible heat engine, that is Carnot engine, multiplied by the heat supplied to the system. So that is something which would be the maximum useful work potential, or in other words, that would be your Exergy due to the heat transfer. So that is what we are going to write here. So the Exergy transfer by heat would be your X heat, and that is going to be your Carnot efficiency multiplied by Q, okay, where Q is the heat transfer at T and T0 is nothing but your surrounding or environment temperature. Okay. Now when T is not constant, that means when T is not constant, what we can do is we can consider X heat is simply your integral of dx heat, or in other words we can write 1 minus T0 by T del Q. So that is going to be when T is not constant. Okay, so let's look at Exergy by heat transfer across this rigid wall. So you have medium 1, medium 2, temperature is T1 higher than that of T2 of medium 2. So heat transfer is given by Q, which is going to be of course constant across this wall. The corresponding entropy transfer is simply your Q by T, okay, for medium 1, and for the case of medium 2, this is going to get increased because T2 is less. So the difference here corresponding to that for medium 1 and medium 2 would be your entropy generated. Now based on the previous definition, your Exergy transfer can be written in this form, 1 minus T0 by T1 Q, and that is going to be more. Okay, note that T1 is more, that means your efficiency, this term is going to be more compared to this term where T2 is less. Okay, so thus your Exergy is reduced here, or in other words, when you compare this medium 1 and medium 2 Exergy, there is a certain amount of Exergy which get destroyed. Okay, that means there is a less amount of useful work after the process, okay, corresponding to the energy remaining in the medium 2. So that was the case of Exergy transfer by heat. Now we will look at Exergy transfer by work. Now by taking an example of a piston cylinder device. So Exergy transfer, okay, by work, okay, would be simply work, okay, in case there is no boundary work involved. So this would be for the case of your shaft work, for example, okay, or for that matter electrical work. However, if there is any involvement of boundary work there, such as what we have seen here for the piston cylinder device, when this particular device does a work during the expansion process, the work is done to push the air, okay, as it moves up, and thus this particular work which does against the surrounding cannot be transferred, and thus this particular or the total work which is useful would be your W minus W surrounding. So this is for the case of boundary work. Well, W surrounding is nothing but P0 V2 minus V1. Okay, but it should be noted that W surrounding, which we have written for the expansion, this would mean that there will be less amount of useful work. For the compression process, we need less amount of useful work from an external source. In other words, during a compression process, part of the work is done by the atmospheric air, and thus we need to supply less useful work from an external source. So W surrounding may mean loss or gain as well. Okay. Next, we consider exergy transfer by mass is going to be simply your X mass is M. This is nothing but psi, which is nothing but flow exergy. Okay, and psi is your H minus H0, as we have already derived earlier or defined this in the previous lecture. So this will be your enthalpy change minus T0 change in the entropy plus the kinetic energy term and potential energy term. So that is for the unit mass case. Okay. So in other words, what we are saying is that the mass contains energy, entropy, and of course now we are saying that the mass also contains exergy, and thus mass flow into and out of system is accompanied by the changes in these particular properties. Okay. Now, as we have already discussed this fact that during an isolated system or during an isolated process, your entropy keeps increasing. In other words, the entropy is being generated, and thus we have defined that your S generation is greater than or equal to 0. Okay. So that we talked about earlier is that is a principle of increasing entropy. Okay. You can make use of this similar analysis and come up with a decrease in exergy principle, which is the alternate statement of the second law. So we can talk about second law in terms of entropy gain, or we can talk about second law in terms of exergy, decrease in the exergy principle. Okay. So in other words, what we are saying is exergy of an isolated system during a process always decrease or remain constant for a reversible process. So we can try to derive this. So we consider an isolated system, okay, for which the energy balance would be simply delta E system is 0 because there is no in, there is no out, okay, because there is no heat, work or mass transfer, and thus E2 is equal to E1. Okay. We can also do this analysis for your entropy balance. So entropy balance would be your again S in minus S out plus S generation is delta E system. This is going to be 0 again because of the fact there is no interaction with the surrounding. Okay, and thus your S generation will be simply S2 minus S1. Okay. Now you can multiply this term by T0. Okay, and what you do is you can multiply this and then you can subtract this from this particular equation, and this will yield this equation. Okay, so if this is 1 and this is 2, then 1 minus T0 into 2 is going to give you this. Okay. Now we know based on the definition of our exergy, the exergy change is going to be simply E2 minus E1 plus P0 V2 minus V0. Now considering this is isolated system, okay, which essentially means that your V2 and V minus V1 is going to be 0, and then you have this term minus T0 delta S. Now after eliminating this term, what you get is this. So if you compare this equation 3 with 4, what do you get? You get minus T0 S generation is nothing but x2 minus x1. Okay, and we know that S generation is greater than and equal to 0, which means this is nothing but less than equal to 0. Okay, so in other words, delta X, which is this for isolated system, is going to be less than equal to 0. This is the derivation which tells you that entropy increase principle for an isolated system, as which is equivalent to second law of thermodynamics statement, is also can be written in terms of decrease in exergy for an isolated system as shown here. Okay, so now we can touch upon the irreversibility aspect and in particular look at exergy destruction. Okay, so irreversibility as we already have discussed earlier, that always increase the entropy. Equivalent statement is irreversibility always destroy exergy. Okay, so this is coming from the fact that X generation is greater than 0, or in other words, your delta S is less than 0. So now the fact is of the irreversibility is because of various different aspects which we already know now, is because of the friction, mixing, chemical reaction, heat transfer through a finite difference, unrestrained expansion, okay, and non-quasi equilibrium compression and expansion. So the statement irreversibility always destroy exergy is now clear for simply an isolated system. In other words, decrease in exergy is your x1 minus x2. Okay, so this is would be the decrease in exergy. This would be your nothing but x destroyed. Okay, or we are saying that x destroyed is nothing but is equal to T0 multiplied by S generation. Okay, so it's very clear that your amount of exergy which is destroyed is directly related to your entropy being generated. Okay, so exergy destroyed is proportional to the entropy generated. Okay, so now X destroyed, okay, this would be your 0 for your reversible process, because your S generation is 0. Okay, is going to be greater than 0 for irreversible process. Okay, because S generation is of course greater than 0. Can it be negative? No, it cannot be negative. So this would be your impossible or not possible process. Okay, now this is very clear that your exergy destruction cannot be negative, though exergy change can be negative, as we already discussed. So now we can extend this understanding and we can apply this exergy balance for the complete system, just as we did such kind of exercises, such kind of balances for energy, entropy. Now we are going to extend this concept to exergy. So what will be the exergy balance? So this will include the transfer due to the heat, mass and work. Okay, and then this will also include any exergy which is being destroyed in the process, and that would finally yield a change in the exergy of the system. So this is a schematic representation of the system. So we have X in, X out due to mass, heat, work, and the concept which we have just developed based on this exergy principle, or the decrease in exergy principle, can be now written in more formally, that total exergy entering minus total exergy leaving minus any destroyed exergy should be equal to the change in the total exergy of the system. Or in other words, we can write this in a general expression in terms of X in, X out minus X destroyed equal to delta X system, or this would be your rate form. Okay, so this term would be the rate of net exergy transfer by heat, work and mass minus X destroyed, the rate of exergy destruction, that will be your change in the, or the rate of change in exergy of the system. Okay, now it should be obvious that for reversible process, as we discussed, that X destroyed is 0. Okay, and hence it should be dropped from the equation. Now exergy of the heat is now very clear that we write in this form. Exergy of work would be useful. Now this would be your W for shaft and electrical work, otherwise this will be your W minus W boundary for the boundary work, or the way the system involves boundary work, and this X mass is simply mass times your exergy of the flowing fluid. Okay, now what we can do is we can do this analysis for your exergy balance for the closed system. So we have considered closed system here, which means the mass contribution is not there. So for a closed system, okay, your X heat minus X work would be your total contribution or net exergy transfer to the system minus your X destroyed. Okay, so that will be your change in the exergy of the system. Okay, so we can further expand this and bring you can write exergy in terms of T0 by Tk. Okay, just the way we have done for entropy balances. Okay, where basically K means the different element of the boundary. Okay, where the heat is being transferred. Okay, and this would be simply your work minus if there is any possible boundary work involved. So that will be your x of work minus x destroyed is nothing but T0 generation. This would be your delta x system, which is x2 minus x1. Okay, you can write this in terms of rate form. For the rate form, you have the same expression except that you have to write dot and W becomes the rate, and P0 dV system by dt, that will be the rate of change of the volume, minus T0 S generation dot, okay, that will be your dx system by dt. So that will be your expression for the rate form. Okay, we can do certain examples now in order to demonstrate this exercise for the Exergy balance. So this is Exergy balance for heat conduction. The atmosphere on the left side of the brick is 27. This could be your room, and this is your outside temperature, which is 0 degree. At the wall is 20 degrees Celsius, and this is at 5. Okay, so one of the question could be is to find out your x destroyed for the system, which could be your wall. Okay, if you can consider this wall as a system. Okay, in that case you can write this expression in this form, where you have heat transfer in and out. So that means contribution of Exergy in and out is due to the heat only. That is written in this form. Then you have this x destroyed. This for the steady state condition, this will be 0, and then x destroyed can be directly calculated. So this will be your Exergy destroyed within the system. Okay, now you can take another exercise, which will be your expansion of steam. Okay, so here you have a piston cylinder device which has initial state is given and the final state is given, and what is being asked is to find out the total Exergy destroyed. Now the total Exergy destroyed would also include the immediate surrounding, because your outside temperature is P0 is 100 kilopascal and 25 degrees Celsius. So if you include surrounding, so that your temperature difference is at the boundary of this immediate plus surrounding, this would become your T0. In that case, if you apply this Exergy balance, then this particular term is going to be 0. Okay, so please note here that x in is going to be 0 because there is no contribution as far as the transfer in is concerned. The out is your x work out, because working against, so this will be your out work on the surrounding. So this would be your work out minus x heat out, which is going to be 0 if you consider extended system, okay, where the boundary is at the environment. Okay, and thus your x destroyed can be written in this form. Okay, W out, useful out, x1 minus x2 minus W useful out. Okay, now we can take another example, which is the Exergy balance of an air tank. Okay, and this problem is the following. So you have a insulated tank with air, and there is a shaft which is applied, and the outside temperature is 20 degrees Celsius. So what is being done is it is being asked to do certain work in order to raise the temperature to 54 degrees Celsius. So what we can do is, or is being asked to find out what is the corresponding reversible work for this process. So what we do is, for the case of a reversible, we know that Exergy destroyed is going to be 0. So you apply your Exergy balance, and this is going to be 0 for the reversible case. So thus, considering insulated, the only thing which is being supplied is your W reversible in, and thus your x in, that is W reversible in, is going to be simply the change in the Exergy, so which can be written in this form. Considering the change in the volume is 0, so you can calculate this, and it turns out to be 1 kilojoules for the case of air considering idle gas. Okay, so this is the reversible work which is required, but if you apply your energy balance, because your energy balance would yield that the work motor or this work paddle wheel work is simply equal to change in the internal energy, and that is going to be 20.6 kilojoules. Okay, so W reversible work is something which is coming out to be 1 kilojoule. So this can be realized by considering that this whole operation can be represented in this form, where the reversible pump is making use of the ambient condition at 20 degrees Celsius, which has 19.6 kilojoule, and it does a work of 1 kilojoules, and thus your final energy change is 20 kilojoules, which is supplied to the air, which changes temperature from 20 degrees Celsius to 54 degrees Celsius. Okay, so that means the same effect on the insulated tank can be accomplished by a reversible heat that consumes only 1 kilojoules of work. Okay, so that is something, the analysis of this based on Exergy. So this will be the end of this particular lecture. In the next lecture, we will be taking this exercise to Exergy balances for control volumes, followed by a few examples. So see you in the next lecture.